Howdy folks. I've been working on a project where I have been mining through an absolute boatload of X-ray timing data looking for measurements of pulsar spin frequency. I've been doing this for a wide variety of different sources to try and catalog and document the evolution of the rotational dynamics of a number of these different sources. In this video, I would like to do an overview of this project to kind of describe what exactly it is that I am doing and how I'm doing it, and to share some preliminary results with all of you. That said, at a link in the description of this video, you can access these catalogs that I've produced for roughly about a dozen different sources, and you'll also find some additional reference material. As always, if you have any questions, comments, or concerns, do not hesitate to ask. But without further ado, let's discuss mining X-ray time for pulsar spin frequency. Alrighty, so rather annoyingly, since I've been working on this project for a little while, just to get things out of the way, I have recorded this on a few different occasions, so I've done multiple different takes, which is something I normally don't do. So if I look different or I sound different, that's almost certainly why. But like I said, I've been working on this for quite a while, and so every time I've tried to sit down and record something and I watch it back, when I try to edit it, I either leave out an important detail, or a detail that I think is really important anyways, or I say something in a way that I don't quite like. That said, I think the best place to start with this is to give you a little bit of background information about how this project actually got started. In short, as a student, as a part of a high-energy astrophysics and astronomy group at my university, I got to do a good deal of timing work and other observing related work, or kind of analysis related work. And when I first got started, or whenever we would try a different methodology or something related to trying to measure nearly coherent oscillations, quasi-periodic oscillations, or, whatever it might be related to, oscillations from a wide variety of different sources, I was told to calibrate those different methodologies with CRAB data from, whichever mission I happen to be working with, and compare the results to the known measurements or the known spin frequencies reported in the monthly CRAB ephemeris produced by the Jodrell Bank Radio Observatory. For those that don't know, for about every single month since the early 80s, the Jodrell Bank Radio Observatory in the UK has measured and cataloged the spin frequency of the CRAB pulsar spin period. I like spin frequency. They're just inverses of one another. Take your pick at whichever one you like, but I'm going to use spin frequency because I like that. But anyways, they've been measuring and cataloging measurements of the spin frequency of the CRAB pulsar, and up to 3 derivatives of that spin frequency, to produce a really, really fantastic catalog documenting the evolution of the rotational dynamics of the CRAB pulsar for quite a while. I think it's, based off the estimated age of the CRAB pulsar, it's almost 5% of the total lifespan, I think, of the CRAB pulsar. If it's not quite there, it's definitely getting close to there. But I was always really unnerved that I was comparing X-ray results to that of radio results. I mean, they're one's high energy, one's low energy. I didn't quite like that. And so after a number of projects didn't work out the way that I wanted to, I started my own project where I just said, hey, I know there's all this XTE PCA science event mode, or good xenon event mode data for the CRAB pulsar. I know there's all this NICER data. There's a few other missions I could throw into this, but I know at least that XTE and NICER gather fantastic timing data in the X-ray band, and so why don't I just produce my own version of effectively what Jodrell Bank has done for the CRAB, but just with X-ray data. And that's what I did. The CRAB pulsar was the first source I ended up kind of applying this methodology to, and then I realized I could expand this out to a number of other sources that I was really, really interested in studying, and at least getting a better understanding of from the evolution of the rotational dynamics kind of point of view. And so that's really largely what this project is. I've been going through and gathering all of the available XTE and NICER data that I can, that I would like to mine through to try and gather as many high-quality measurements of spin frequency as I can from that data to produce a similar catalog for sources like the Crab, for sources like Pulsar J0030, Hercules X1. The list really does go on quite a bit, and I think there's about a dozen I've done so far. Now, for every single source that I've decided to mine through, I've literally tried to go through and gather all the available XTE and NICER data sets, and in particular with the XTE data, I am going through and looking at PCA science event mode and good xenon data. More on that in a minute. This entire data mining project and procedure follows a simple 3-step data mining pipeline, which is really only 2 steps because the last stage is filtering and further verification or validation. So, stage 1, data gathering and data preparation. It's pretty straightforward. I am gathering all the available XTE and NICER data from the XTE master and NICER master catalogs over at the HEASARC. Big shout out to all the folks at the HEASARC, and especially all the folks with Heasoft. Couldn't do this without any of you guys doing, whatever it is that you do over there. You just work your magic so that I can access all this awesome data. And of course, anybody associated with those 2 missions, it's fantastic. By the way, not to go off on too much of a tangent, but I do know that there are possibly other missions that I could gather this data from, but I chose XTE and NICER particularly because they are really fantastic at gathering high-quality timing data. XTE ran from 1995 to 2012, really. It's 1996 because it's December 1995 to 2012, but anyways, and it was capable of, I think, as good as 1 microsecond of timing resolution. NICER, of course, is still in operation. It's been in operation since 2017 and is capable of, I think, as good as 300 nanoseconds of timing data. Again, I don't have that data necessarily in front of me, but I will, of course, overlay it on the screen. And to make this as speedy and as easy as possible, I created 2 different tools in order to accomplish gathering and preparing this data. Not to mention that with preparing and gathering as much of this data as possible, I want to prepare it appropriately, but I also want it to be as simple as possible and as streamlined as possible so that I'm not dilly-dallying around. These 2 tools are Auto NICER and Auto XTE. I know, very creative names, but that's what I came up with at the time. Auto NICER I've discussed on this channel here before, and it's pretty simple. It's both of these tools are just live on top of a local installation of Heasoft and allow you a really simple CLI interface to select whatever observation IDs you want to gather, and then they get pumped through a very simple and streamlined data reduction process. In the case of NICER with Auto NICER, you could, just select whichever obs IDs you want, select by cycle, select all of them, who really knows, who really cares, and then it just, that gathered obs ID data set then gets pumped through NICER L2, clobber equals yes. There's nothing really fancy going on with that. Then, of course, there's also a bury center correction that is done that is really important, and it is done in the following way that you're seeing on the screen right now with the JPLH 430 ephemeris orbit files as they appear in the auxil directory and the right ascension and declination as they come from the NICER master catalog. Then, with those bury center corrected MPU7 cleaned event files, I just strip out the photon arrival times pretty much, and they are ready to go into the second stage. As a matter of fact, it's the entire event file that gets passed into the second stage, but it's really only the photon arrival times from that event file that I'm needing. A similar thing is done to the RXTE PCA SE or GX event mode data. Now, with RXTE, I'm taking a little bit of a different approach, and I'm taking a little bit of a shortcut because preparing data for RXTE data is not necessarily as straightforward as NICER, with just having the great, awesome NICER L2 pipeline that I can just pump everything through, and it does all the calibrations, all the filtering, merging, whatever it is, that goes on in NICER L2. This video is not one where I'm going to go through all that, but there isn't really anything like that exists for RXTE, and so I took a little bit of a shortcut, and that shortcut is that while I was looking through the HEASARC and I was looking at a wide variety of different RXTE science event mode or PCA science event mode or good xenon event mode data, so our SE or GX. I'm just going to call it SE or GX from now on because I hate saying the whole thing out loud. I started to notice that a lot of that data, whether it was cycle 4, whether it was cycle 10, whatever, it doesn't matter when it was gathered, a lot of those particular files were last modified in 2012 after the RXTE mission had ended, or just very near to the end of the RXTE mission. And I thought to myself, why exactly is this happening? I looked all over for documentation as to why this is actually a case, couldn't really find anything. And so me overthinking this, of course, way too much, and looking for a shortcut that I admittedly didn't want to have to prepare all this data by hand manually, thought to myself, why would all of these files be last modified in 2012? Maybe there was just a changing of metadata or things moving around on the server, but I thought to myself, if I was in the shoes of somebody over there with the RXTE mission, at the end of the mission, I would want to re-prepare all of the existing data to be properly archived, so that anybody who might want to access it can just go in and grab that data and start to use it, and have that data already pre-prepared with the latest calibrations and the latest software with all the different bug fixes and whatnot that is in there. And so that's the assumption that I'm making with this. Again, I have kind of gone all over the place, and maybe I am completely missing something here, but that's the assumption that I'm making, that all of this data is good to go, and actually judging from a lot of the results, it indicates that it probably is good to go. But all Auto XTE does is it is grabbing the entire RXTE OBS-ID dataset, and it's looking for science event or SE or GX event mode data, and then if it finds it, it is applying a Berry center correction to that data in the following format that is slightly different from Auto NICER and slightly different from conventions, I believe, if I understand correctly from other conversations I've had with numerous other people. But nevertheless, it is basically just taking all those files, producing a Berry center corrected version of that file, and then all of that data is then getting pumped out and piped right into the second stage. So stage 2 with this is actually mining out the spin frequency, and the technique for doing this, at least with X-ray, that I'm using is known as the ZN squared statistic. A really fantastic paper that I've kind of been using as a reference to go off of this is by Craig Markwardt and Tod Strohmayer for the 4U 1636 source. Anyways, it's a fantastic paper. They do use the ZN squared statistic in there. And so let's talk about this ZN squared statistic in a little bit more detail right now. What you're seeing on the screen is the ZN squared statistic, and when you pair it with the corresponding phase model, this is a really, really powerful statistic or algorithm, because what it's effectively doing is it is doing basically a Fourier transform, but instead of just an arbitrary gain that you're getting from these results, you end up getting a statistical interpretation of just how well a given phase model fits to the arrival times of the data set. And so let's actually just start this off with the phase model. So this is just a simple phase model right here, where T naught is the first photon arrival time of a given observing interval. Those observing intervals are very unique, and you can get into the weeds with that. We definitely will, maybe in some future discussions that I have with these. But Ti is each subsequent arrival time. Then, pretty simply, since I'm just going after the spin frequency, we don't need to go past 0 with order here, since we're not going after the derivatives, at least not yet. Anyways, nu is going to be the spin frequency. We don't need to go past 0 with order. And so what we'll do is we'll just compute a collection of these phases for a specific test spin frequency, and we'll do this for a wide range of test spin frequencies that we want to do. So for example, like with the crab, I know that the crab is going to spin somewhere between 29.5 and 30 hertz. So I'll set a range of 29.5 and 30 hertz, and I'll do that generally, for this project, I'll do that anywhere between a resolution of 10 micro hertz and 100 nanohertz. Generally speaking, I'm not really dipping past about a microhertz, but that's kind of the range that I've been working with a lot of these different sources. Then with these phase models, we can throw that into Zn squared, for a given spin frequency, and it will go through and it will spit out a value for us that is statistically equivalent to a chi-square with 2n degrees of freedom. By the way, big N here in Zn squared is the total number of photon arrival times for a given observing interval. But Zn squared, like I said, is statistically equivalent to a chi-squared with 2 little n degrees of freedom, where little n is the number of harmonics we want to introduce into our domain. And so, for me, I'm not really going past, the one harmonic. So, for Z1 squared, that's statistically equivalent to a chi-square with 2 degrees of freedom. And when we compute, these Z1 squared values for a wide range of test spin frequencies, and we distribute them all out, it's basically just like a power density with a conventional Fourier transform. And that statistical information gives you a really, really useful bit of information to go ahead and look at this and say, okay, ideally we have some type of Gaussian shape here, as you would expect from like a Fourier transform. And so the peak of that would be our measurement of spin frequency, and then full width half max would be our error bars. Although I want to point out here that what we're doing is we're not really measuring the spin frequency. And that's why, it is a measurement, but not really, because what we're doing is we are fitting a collection of phase models for a given spin frequency to our photon arrival times, and we're seeing which spin frequency fits best to our photon arrival times. And so this is really just a game of model fitting with statistics to back up which model for phase is fitting best to our to our observational data. This second stage is called slooshing, and the term slooshing is actually borrowed from conventional mining and has been applied to data mining in this case. Actually, as a matter of fact, more broadly speaking, the term slooshing is used when discussing this type of timing work, whether you're using Zn squared or some other type of methodology or whatnot. But to better understand what's actually going on here, let me briefly explain what slooshing is in the conventional mining context so we can understand how it applies and understand exactly what's going on in this situation. In the context of conventional mining, like say mining for gold, the process of slooshing is taking your material that you think may contain gold and putting it through something like a sloosh box. In doing so, it is going to separate out the light material that is likely to not contain any gold from the heavy material that is likely to contain the gold. Once slooshing is complete, you'll be left over with a bunch of heavy material that will be a lot easier to go through, in which you'll be able to extract that gold. And in the context of this, what we're doing is we are taking a wide variety of test spin frequencies and we are putting it through the Zn squared statistic. In doing so, we are trying to separate out test spin frequencies with little to no statistical evidence for their existence in the frame during a particular exposure from the test spin frequencies where there's a great amount of statistical evidence for them existing in the field of view during a particular exposure. All of that is really just to say that there is additional filtering and cleanup work that needs to go into play here. All this is statistical evidence of oscillations in that particular field of view during that particular exposure. As a matter of fact, like in the case of NuStar, you can have evidence of oscillations that are not even necessarily related to anything that's in the field of view, but that's related to the instrumentation of the mission, and that's largely why I'm not going through NuStar data. This isn't really much of an issue with XTE or NICER, though. One of the things we can do if we want to see whether or not the peak of our Gaussian or the best fit test spin frequency is actually related to the spin frequency of the pulsar is we can produce a phase-resolved light curve, or better known as a pulse profile. We can do this by taking our phase model and fixing that best fit test spin frequency to be nu, in this case, and then we can run all of our photon arrival times through this again, limiting the phase computation to be between 0 and 1. Then we can take all of those phase values and bin them up and create a histogram, in which case you can see, like here for the Crab pulsar, where we see a nice, clear, coherent pulse profile for the Crab pulsar, which indicates that our best fit test spin frequency is the spin frequency for the Crab pulsar, because there's this corresponding pulsation that we can see from the pulse profile. And so really, I should probably include a stage 2.5, which is computing this pulse profile here. But I'm doing that for every single result that I am getting that is showing over 5 sigma in statistical confidence, or a chi-squared with 2 degrees of freedom, or z1 squared, greater than or equal to 30. But clear evidence of pulsation, or a nice clean pulse profile, is not always present with every single one of these results. That doesn't mean we can just easily throw out these results. For a large majority of these results, I'm just going off of the statistical evidence that's there, and I'm using the good old tried and true, very unscientific saying that if it looks like a duck and it quacks like a duck, then it's a duck. And so, much like I was comparing results from Jodrell Bank with radio to, what I got, from the X-ray with the Crab pulsar, if it looks like the spin frequency and there's really great statistical evidence, like as is the case in many cases, like with the Crab pulsar, then it's fair to assume, at least I'm making the fair assumption, that it's a spin frequency. But I do understand that that's not necessarily evidence of pulsation, and it could be from a whole litany of other things. As a matter of fact, there's all different types of evidence that comes in of a whole wide variety of different timing noise. But you can see it's very Gaussian in nature, but it's very, very noisy. And so 4 with half max could probably still work here. A peak could probably still work here. But fitting a Gaussian to this might be more appropriate, and using that fit Gaussian might be more appropriate. But then there's also examples like this, where you have like this weird kind of like harmonic, like, who knows what that timing noise is related to. Or even worse, you could go ahead and get something like this, which isn't really Gaussian in nature. It's very choppy. It's very, very noisy. And, who knows what these other 2 spikes are on the other side of it. As a matter of fact, this looks much more Lorentzian in nature than Gaussian, but even that isn't probably an adequate description of what's going on here. So there's also even examples with other sources that are binary sources that may be accretion-powered millisecond pulsars, and you get this type of noise here where you see a build up to the best Gaussian, if that's what you want to call it, or you see a build down from that best Gaussian, and that noise could be related to the accretion, that could be related to the fact that many of these sources are transient sources, so we're observing these in outburst, or it could just be noise due to and related to the fact that this is in a binary orbit, and you're picking up some of that in the actual, work where we're looking here for oscillations, because remember, this is just statistical evidence of oscillations. So hopefully you can see that determining what goes into these catalogs is kind of subjective, or at least it's maybe it's not subjective, but it's kind of, I don't want to say complicated, but that's where the third stage kind of is, and that's with the filtering and cleaning or validation or whatever. With a lot of that timing noise, some of the stuff can be salvaged by just fitting a Gaussian to it, and then using the fit Gaussian result compared to the noisier result, if that's what you want to call it. But in some cases, some of those results should just be completely thrown out, even though there is actual evidence or statistical evidence in there of oscillations. Also, too, you kind of want to take everything with a pinch of salt with the, whole, if it looks like a duck and quacks like a duck. I don't know that you even want to call it a methodology, but just idea, I guess, if you will, for keeping some of these data points into the catalogs. And so that's why I've set up the these catalogs and the web dashboard in the way that I did, and so that you can go there, you can filter things out for yourself, and you can download a filtered version if you want to. You can also just download an unfiltered CSV of all these results, and you can just go through and write your own code to filter them yourself if that's really what you decide you want to do, although you're not going to have each one of those individual measurement plots for the oscillations and then the phase resolved light curves there as well. And so going forward with this project, what I want to do is I want to basically start making videos for each one of these sources and kind of describe why I chose to go through these sources, why they're interesting to me, and then document for you how I am going about filtering them on my end for my own use cases in other projects and different areas of where I'd like to jump off into other areas. I'd also like to go after derivatives, but that is not necessarily as straightforward as the test spin frequencies. And also, I'd like to discuss some of the engineering that has gone into this project to really make it much more practical to where, I'm able to go through a lot of this data much, much faster. I think of all of the X-ray data that I've gathered, I've probably gathered over 4 or 5 terabytes. Additionally, this is a methodology that could be applied or expanded upon further to look at some other sources that we might suspect to be pulsars, but we don't necessarily have evidence for pulsation or oscillations from just yet. All that is to say that I want to make a lot more videos and discuss this topic a lot more, because it's been something that I've been working on for quite a while, and I think that it's something that I would like to share with you, as I know there's plenty of all of you that are going to be interested in this and have a conversation about how I might go about filtering these things and where I might take some of this stuff going forward. And I'd like to say that all of this really wouldn't be possible if it wasn't for my research advisor giving me the chance to join her team way back in the day, Dr. Sachiko Saruda. Yeah, I mean, an absolute living legend. I mean, she's been studying pulsars and neutron stars since before Jocelyn Bell and all of them even really confirmed to us or provided evidence that pulsars and neutron stars are real things, really. But of course, I can't just thank her. I also have to thank Dr. Andrew C. Liebman for, really teaching me how to, work with Heasoft and really helping me understand some of the astrophysics and astronomy side of things. And last but certainly not least, I need to thank Dr. Marcus Teeter for his ongoing conversations with me about this project. He's the one who originally showed me a fantastic paper by Craig Markwardt and Tod Strohmayer on this topic, which kind of really made me look into this Z squared methodology. And I wouldn't be doing any of this right now had he not shown me that paper and had he not continued ongoing discussions with me about this project. I know he's definitely very interested in it as much as I am. So big thank you, Marcus, if you do happen to see this. I'd also like to thank all of you. If it wasn't for some of the fantastic conversations and some of you great folks who have reached out to me over the past few years of making a bunch of different videos, whether they be math-related, physics-related, astronomy, astrophysics-related, I do feel like this is probably the best way for me to put this information out into the world at this current juncture in my life. I am not in academia. I do this on my own time, on my own dime. I'm unaffiliated. I don't plan on being affiliated with any large academic institution, really going forward, unless something significantly changes, and I don't want to go on a whole rant about that. And the fact that I've been working on this for a number of years, and I've never published it anywhere, I've never put it out anywhere, has just kind of made me rethink and just say, you know what, this is in a good enough state where I want to share this with the world, and that's exactly what I'm trying to do with this. So if you want to have any input, if you have any questions, comments, concerns, any of that type of stuff, don't hesitate to reach out. Plenty of you have gotten very creative in the ways that you've found ways to reach out to me, and I do appreciate being able to nerd out with all of you, because living in rural America, I don't really get too many opportunities to nerd out with people unless it's like ongoing conversations like I've stated before with Dr. Marcus Teeter. But all that's just to say, thank you all very much for watching. It does really mean a lot. when you do interact, and when I do get to communicate with all of you. And I know that I find this work of value. I know I find it interesting, and if I know that it's of value to me and I find it interesting, I know there's plenty of you that will also find it valuable and will also find it interesting. So that said, thank you very much for watching. If you've made it this far, there's much more to come on this topic, and so thank you very much again for watching, and I'll hope to see you again next time.